Okay, you're good. Okay. Hi, everyone. Sorry for the delay. My name is Gabriela Silva, and as many of you already know, I'm a PhD candidate in biostatistics. I'm in my third year of my degree, so hopefully it won't take too much longer to finish up. I did my undergraduate in math and economics. I ended up at Brown doing biostatistics because I like the more applied part of math, and I wanted to be able to apply my mathematical knowledge to more public health and public policy related issues. In my time at Brown, I've been working on numerous research projects. One of these involves research at the VA, looking at mortality outcomes and the impact of using different risk adjustment methods. And then my dissertation work is on profiling providers and examining like the impact that different statistical methodologies have on the quality of care that's being estimated. Today we're going to be talking about hypothesis testing. So if anyone has any questions throughout, please interrupt me or we can take questions at the end. So I wanted to start out with a motivating example because I think this is going to help us understand and get an intuition for where you might want to be using a hypothesis test. Suppose that you know that the population mean serum cholesterol level for a specific group of men is 211 milligrams per 100 milliliters. And as a researcher, you're interested in knowing what the average serum cholesterol level is for a subpopulation of this group. So for hypertensive smokers, you're interested in knowing what their average serum cholesterol level is. So in order to answer a question like this, you're going to have to ask whether or not you have any evidence that's showing whether the average serum cholesterol level for hypertensive smokers is the same as that for the general population. So essentially, does it equal 211? And since we're all going to be acting like scientists, in order to address this question, what we do is that we go out and we collect a sample of hypertensive smokers, let's say size N, and since we're going to be shooting like a group of hypertensive smokers. And then once we compare, based on this comparison, we're going to be able to decide, are they different or are they the same? But the truth is, determining how different is different enough is actually a little bit challenging. And so that's where hypothesis testing comes in, because it allows us to quantify how different is different enough. So for example, if I tell you that in my sample, the mean serum cholesterol level is 210, then some people might say, oh yeah, that's super different than the population average of 211, while other people might say, no, that's the same thing. A hypothesis test is going to allow us to quantify that difference. So a hypothesis is essentially a claim about some population parameter. Throughout this talk, I'm going to be focusing on mostly averages. A hypothesis test is a method that we use in statistics and in many other disciplines that involves using sample data that you've collected to decide between two hypotheses. The first of these is the null hypothesis, which is usually denoted by H0. And the second of these hypotheses is the alternative hypothesis or alternate hypothesis, which is usually denoted by an HA. Or sometimes it's actually called H1 as well. The null hypothesis is going to be what you originally assumed to be true, but you're trying to test. And the alternative hypothesis is what's going to challenge this null hypothesis. So going back to my motivating example, the null hypothesis would be that the subgroup of hypertensive smokers has the same average cholesterol level as the population, so that it's equal to, I think it was 211. And the alternative would be, no, they're not equal, they're different. So these steps here, I included them because I think they help formalize the idea that conducting a hypothesis test is a lot like conducting a scientific experiment. The first thing you're going to do is you're going to formulate your hypotheses. In a hypothesis test, we usually have two of these, which are the ones I just explained. H0, the null hypothesis, and HA, the alternative hypothesis. Once you've formulated these, you're going to go into your population of interest and collect data on them. And this data is going to be evidence that's going to help you show which hypothesis there's evidence for. And then in the third box is actually the hypothesis, like conducting the hypothesis test. So we use ideas from statistics to help us quantify just how different is different enough. And then in the fourth step, you draw conclusions based on the results of your hypothesis test. So one thing that I want to make sure is very, very clear is that when you're specifying this null and alternative hypothesis, so when you specify H0 and HA, they need to be able to cover all the potential outcomes. So what I mean by that is that either the null or the alternative must be true. There can't be some third other potential outcome. So again, returning to our motivating example, if I say that the null is that the subpopulation of hypertensive smokers has the same average as the general population for serum cholesterol, then the alternative is that these values are just different. And in this situation, the null and the alternative are properly specified because either they're the same or they're different. There's no other potential outcome. And so the goal of a hypothesis test is to determine, okay, is the evidence in favor of the alternative or is it in favor of the null? And so again, I included this illustration because I think it helps us show what a hypothesis test is trying to do. Originally, you're a scientist, so unless you have a lot of preliminary data, you should be assuming that they're somewhat balanced. Originally, the null and the hypothesis and the alternate hypothesis are most likely equally likely. But then as you go and collect evidence and you collect data, the balance might turn in favor of one or in favor of the other. So in this case, the evidence has gone in favor of the alternative hypothesis. And so a hypothesis test is trying to quantify which direction we're going in. So as I mentioned, there's two potential outcomes of a hypothesis test. And I'm going to be emphasizing this a lot. The language that you use when you're concluding things about a hypothesis test is very important because there's like some intricacies involved, and it's important to make sure that we understand what exactly the hypothesis test is showing. A hypothesis test, you're either going to be rejecting the null in favor of the alternative, or you're going to fail to reject the null. Those are your two potential outcomes. You might want to reject the null in favor of the alternative when the probability of observing a value as or more extreme than what you observed is very, very small if you were to assume the null. So that's a lot of words, but what I mean by that is, going back to our motivating example, if I assume that the two populations, so the subpopulation of hypertensive smokers and the general population, have the same mean, and then I go and collect data, and the mean is vastly different than what I've assumed. So let's say I collect data, and the average level is like, I don't know, 190, and you assume that it was 211, then the probability of observing that 190, if you assume the null value, is really, really small because that's really far away from 211. And so that might mean that you might want to reject that null hypothesis. Conversely, you might want to fail to reject the null in a situation where you collect your sample of hypertensive smokers, and you find that the average value is 210.5, let's say. In that case, the sample mean is so close to the null value, which is that 211, that the probability of observing that 210 is actually pretty likely. And so in that case, you might fail to reject your null. And again, being really particular about the language, there is a difference between saying that we accept the null and failing to reject the null. So that second potential outcome, we need to be careful and always say that we're saying we fail to reject the null, not that we're accepting the null. Because accepting the null is actually a stronger statement. We're saying that we know that the null hypothesis is true, while failing to reject the null means that we just don't have enough evidence, or our sample hasn't brought us enough evidence to reject the null. And so it's a very slight distinction, but I'm hoping that the analogy I'm going to present next is going to help illustrate that distinction. So essentially, the reason why we can't say that accepting the null and failing to reject the null are the same thing is because our test is going to be based on samples of data. We're not going to be able to gather the entire population of, say, hypertensive smokers. We're just going to be taking a sample. And so our sample is only enough to show us whether or not the alternative value is plausible. It's not enough to prove or disprove the null hypothesis. So the analogy that I was hoping we could focus on would be with the US criminal justice system. And I'm sorry for how it appears. You can kind of read it, I think. So maybe it's just the slide. It's but
the projector because the...
Oh, okay.
The projector, I'm sorry.
Okay, I'll try to be super clear. If there's something you can't see though, like just call me out on it. Okay, so the analogy is the US criminal justice system. So in 2005, in a very high profile case, they found that Michael Jackson was not guilty. That's what the jury decided. And notice here that the jury saying that he was found to be not guilty isn't actually saying anything about his innocence. It's making a statement about the amount of evidence that there are to prove his guilt. So what the jury is actually saying is not, oh, Michael Jackson is innocent. They're saying there's not enough evidence for us to prove beyond a reasonable doubt that he's guilty. So even though that's a very slight distinction, it's an important one. So again, here, we're going to continue this analogy between the US criminal justice system and hypothesis test. So in a criminal trial, the defendant that is up on the stand is either innocent or guilty. There's two potential outcomes, innocent or guilty. And then the outcomes of the trial, the verdict, is that he's either not guilty or guilty. And a hypothesis test works very, very similar because the truth about the hypothesis is that since the hypothesis needs to be defined in such a way such that one of them is true or the other one is true, the hypothesis itself, either the null is true or the alternative is true, one or the other. And when you're conducting a hypothesis test, as I mentioned, there's only two potential decisions you can make. You can either fail to reject the null or reject the null. So having outlined things like this actually helps us visualize when we're going to be making mistakes and when we're going to be correct. So for example, with the criminal trial case, if the defendant is innocent, but the verdict is that he's guilty, we're going to be making that the trial didn't really do its job, like they made a mistake. And on the other hand, if the defendant is guilty, but we say that he's not guilty, again, a mistake has been made. In hypothesis tests, it's the same sort of idea. If the null is true, but you end up rejecting the null, then that's a mistake that you've made. And similarly, if the alternative is true, but you fail to reject the null, then you've also made a mistake. And these mistakes are actually really important and have really big implications in a lot of the research and the confidence levels that you end up coming up with, those p-values that people like to talk about. So I'm going to start discussing those mistakes very soon. So I wanted to provide another example, which also I think will help illustrate these ideas behind hypothesis tests. If we consider this data set, which has just 100 randomly selected runners from this 10-mile race that was completed in DC, upon having looked at this set of 100 randomly selected runners, the researchers noticed that for this set of runners, which was collected in 2012, they felt like this set of times was different than the set of values that they found for 2006. So they were saying, we know that in 2006, the average time for completion of this race was 93.29 minutes. But they were thinking, you know, the 2012 times look a little bit different. Even though they didn't have the full sample of runners, they had this subset of 100 randomly selected runners. They were thinking that it might be different. So in a situation like this, you could also conduct a hypothesis test. The null in this case would be that the average time is the same. So that the average time in 2012 is equal to the average time in 2006, which is 93.29. The alternative hypothesis in this case would be that the average times were different. So the average time in 2012 is not equal to 93.29. So when we're conducting these hypothesis tests, we call this 93.29, or the average value in 2006 in this case, the null value, because it's going to represent the value of the parameter if we find that H naught is true. And so since we're scientists, what the researchers decided to do is that they took this data set, which was comprised by 100 randomly selected runners, and they found the average time for completion of this 10-mile run. And they also found the standard deviation. So when they found the mean, notice that the average time is 95.61. And if we compare it to the null value, or the average time in 2006, we can tell that they're different. But again, there's this idea of how different is different enough. Because the value that they completed, this X bar, which is 95.61, is based on a random sample. So that is not the true 2012 average race time. That's just based on a sample. So when you're estimating something, there is some uncertainty associated to it. So prior to saying, oh yes, they're different, we need to make sure that we take care and account for that uncertainty in estimating that X bar equal 95.61. So again, there's this idea of, we can see that the average time in 2012 is different than the average time in 2006, but how different is different enough to conclude that there is in fact a statistically different difference. So one way to test hypotheses are using confidence intervals, and I know that we haven't discussed this in these seminars yet. I think it's coming up in the next data analysis seminar, but the general idea behind a confidence interval is that it's going to be capturing this idea of uncertainty in our estimate. So as I mentioned, this 95.61 is just an estimate. We don't know the true value of it. So we need to be able to capture this uncertainty, and a 95% confidence interval allows us to do this. So when you have a sequence of points, the 95% confidence interval for the population mean is going to be this X bar minus this T value times the standard error, and the upper bound is going to be X bar plus this T statistic times the standard error. And I know again that we haven't covered it, but this will be covered. And the idea is that, yeah, you're again it's going to create an interval where the center is going to be X bar, which is at 95.61. And it's going to create an upper bound and a higher bound for this value. So if you go through and plug in the values that I've given you, you end up finding that the 95% confidence interval for the average time in 2012 is bounded between 92.48 and 98.74. So the way in which we link confidence intervals and hypotheses testing is that to decide what the outcome of our hypothesis test is going to be, we need to ask ourselves, okay, does the 95% confidence interval for the average time in 2012 include the average time in 2006? And as you may have noticed, it does in fact include this value. And so what this tells us is that we cannot say that the null hypothesis is implausible, because the null value, which is 93.29, falls within the plausible range for the average time in 2012. So after having conducted this hypothesis test using confidence intervals, we say that we failed to reject the null. We do not have enough evidence to suggest that the time in 2006 was actually different than the time in 2012. And again, I'm sorry for saying this so many times, but the result of this test is not saying definitively that yes, 2006 and 2012 running times are the same. What it's saying is that based on the sample, we can't conclude that they're different. So I alluded to this concept when I was talking about the analogy between the US criminal justice system and hypothesis tests. Unfortunately, our hypothesis tests are not always going to be perfect. Sometimes we're going to make the right decision, and other times we're going to make the wrong decision. So as I mentioned, if the true state of things is that the null is true and you fail to reject the null, then you did a great job because you got it right. By failing to reject the null, it means that your hypothesis test has concluded that there's insufficient evidence to reject the null, which is the right decision in this case because we assumed the truth was that the null is true. Similarly, if the alternative hypothesis is true and you reject the null and move in favor of the alternative hypothesis, again, you've done a great job because that is the true nature of things and you got it right. The reason, the point where mistakes start to come in is when you make one decision, but the underlying truth is different than that decision. So for example, if the truth is that the null is true, but you end up rejecting the null, then that's what we called a type 1 error. So that's the probability of rejecting the null given that the null is true. On the other hand, if the alternative is true, but you fail to reject the null, you've made another mistake. And that mistake is quantified as the type 2 error, the probability of failing to reject the null given that the alternative hypothesis is true. Yes. That's a super good question. Because I also sometimes have trouble remembering. I don't know if this helps, but you know when you talk about like p-values and 95% confidence intervals and those alpha equal 0.05, there you're always capturing the type 1 error, and alpha is 1. So that helps me remember it a little bit because I'll talk about this in a little bit, but yeah, alpha, which is usually set to 0.05 or in some clinical studies to 0.01, is capturing that type 1 error. That helps me remember it. But yeah, I can say it again. The type 1 error is the probability of rejecting the null and moving in favor of the alternative hypothesis, given that the null is true. So you've made a mistake because you're basically suggesting that there is, let's say, some sort of difference between the null, the values being tested, when in fact there is no difference, because that's what your null was saying. That's a good question. I actually really always have troubles remembering them too. Sorry? Yes, there's a lot of stuff about like how to interpret a p-value. So it's not exactly that, but the alpha, when you're saying like you want the p-values to be less than 0.05, you're basically saying it's analogous to your type 1 errors. When you're making alpha equal to 0.05, you're trying to limit the amount of type 1 errors that you make. That's a great question. So unfortunately, what we'd want to do is actually minimize both the type 1 and the type 2 errors so that most people can be placed into these green boxes. But unfortunately, similar to the concepts of sensitivity and specificity, there is a trade-off between these two error rates. So usually a test that has a lower type 1 error rate tends to have a higher type 2 error rate and vice versa. So yeah, we don't have, for most things, we don't have a perfect test that's going to make no type 1s and no type 2 errors. So finding the right balance is really what's necessary. And what makes this a little complicated, I think, is that the right balance really depends on the application. So in some cases, making a type 1 error is going to be horrible, and in other cases, making a type 2 error is going to be considered worse. So determining where you want to set that trade-off is really, really important. And I think that understanding how the right balance might change from one application to the next is actually, again, highlighted in this US criminal justice system analogy. If we let the null represent that the defendant is innocent and the alternative be that the defendant is guilty, then what this setup is going to imply is that if we reject the null, then that's going to mean that the people have decided that it's a guilty verdict. So the person's going to go to jail. And so that just kind of helps understand the setup. In this case, a type 1 error, which would be rejecting the null given that the null is true, would mean that an innocent person is going to go to jail in this setup. On the other hand, a type 2 error is going to be letting a guilty person go free. And the way that the criminal justice system is set up, in theory, defendants need to be proven guilty beyond a reasonable doubt. And just by reading that line, you can tell that here a type 1 error is considered worse than a type 2 error in the sense that the justice system is going to prefer to let someone who's guilty go free as opposed to putting an innocent person in jail. And yeah, and I don't think that they talk about like, oh, we want to minimize our type 1 errors, but it's the same sort of idea. The standard amount of evidence that's going to be needed to prove that a person, to give someone a guilty verdict or rejecting the null is going to be very, very high because they just don't want an innocent person to go to jail. They don't want to be making these type 1 errors. So similarly, moving away from the criminal justice system, there's some other examples of these decision errors. So if you're looking at a study that's going to be determining whether a gene is associated with weight loss, then if you let the null hypothesis be that this gene does not regulate weight loss and the alternative be that the gene does regulate weight loss, then a type 1 error in this situation would involve detecting a false association. So detecting that the gene does regulate weight loss when it in fact doesn't. And I don't know too much about genetic testing, but let's say that you detect this false association and then all this money, since you've detected it, all this money is immediately invested into this research for this FTO gene, then rather than going to, I don't know, saving others, then that could be the cost of this type 1 error. And that needs to be weighted against the cost of the type 2 error, which is failing to detect a true association. So for example, if this FTO gene does in fact regulate weight loss, but the result of your hypothesis shows that it doesn't, then potentially if you could have somehow used this gene to prevent obesity and therefore deaths, then this is the cost of the type 2 error. So you need to be thinking in setting the standard for what's going to be a decision where you reject the null and what's going to be one where you don't. You need to be thinking about what are the potential implications of all these errors. So hypothesis testing depends strongly on, as I mentioned, the evidence that we have against, against rejecting the null or failing to reject the null. So we don't want to be rejecting the null unless we have a strong amount of evidence showing that the alternative might be true. And again, the amount of evidence that you need is really going to depend on how you weigh these type 1 and type 2 errors. So a lot of the time, as I was mentioning a little bit earlier, a lot of researchers and clinicians say that they don't want to incorrectly reject H0 more than a certain amount of time. So I know in statistics, a lot of times this is set to 5%, but I know in other applications, in some clinical fields, it actually is much lower, so it's 1% of the time. So they're saying, they're putting more of an emphasis on having very, very low type 1 error probabilities, because the lower this number is, the lower type 1 errors we want to be making. So for now, you're going to hear me be saying like 5% a lot. I'm just going to assume that alpha is 0.05. But you'll see in another slide that, yeah, it can vary from anywhere between like 0.01 to 0.1 in most applications. And we call this alpha the significance level. Alpha is the probability of that type 1 error. And the reason I'm mentioning this now, but we will discuss it in the later talk, when I was showing the connection between confidence intervals and hypothesis testing in one of the motivating examples, I just want you all to notice that that 95% confidence interval, which is what I had computed, but I didn't tell you, that's going to be corresponding to an alpha of 0.05. So another way of conducting a hypothesis test, aside from using these confidence intervals, is by determining, it's called the critical value method, and it's basically involves determining some sort of rejection region. So in the case that we're examining with these population means, the rejection region is going to be the range of values for the sample mean that you've estimated for which you're going to be rejecting the null at a given level of alpha, so at a given level of our significance level. And what alpha is going to be driving is the position of that Z alpha. So let's say that let's say alpha is 0.05, then Z alpha is going to be right there. But if I make alpha smaller, so let's say Z alpha is 0.025, then it's going to be located to the left of that Z 0.05. And what that's implying is that my rejection region is going to get smaller, because if I put a value right to the left of the alpha, you can see that the rejection region is going to be smaller than my original alpha of 0.05. So this is why the rejection region is going to depend both on your significance level, as I just mentioned. Changing that alpha value is going to affect the position of Z, and it's going to also depend on the alternative hypothesis. So what I've pictured here is actually a one-sided alternative, where your alternative hypothesis was that the population mean is less than your null value, and that's a one-sided alternative. But another alternative is that you might want to test if the population value is greater than some null value, and that's the image on the right-hand side. In that case, our rejection region is going to be located to the right of these Z values. And I know I'm being a little bit hand-wavy about the Z's, but essentially they're just values that vary depending on your significance level. So just to reiterate, in the case where you're testing, or your alternative hypothesis is to test whether the mean is less than the null value, then your rejection region is going to be on the left side. And if you're testing whether it's greater than the null value, it's going to be on the right side. Sorry? Oh, the hypothesis testing that I'm going to talk about now is the critical value method. It goes like hand in hand with using confidence intervals. Usually when hypothesis testing is shown, they show the critical value method first, but I actually think the critical value method takes like a little bit. For me, the confidence interval is very intuitive, like does it fall inside of it or not? But yeah, the critical value method is usually what's used with these rejection regions. The rejection regions are going to vary depending on your value of alpha and your specification of the alternative. So these are both considered one-sided alternatives, and the motivating example was actually a two-sided alternative, where we were testing are the means for hypertensive smokers the same or different to the means for the general population. So when you have a two-sided alternative, again, your rejection region is going to have two sides, and it's going to depend on alpha. So as I mentioned, another alternative to conducting hypothesis testing is using the critical value method. And the procedure involves first specifying your two hypotheses. So specifying what your null is and what your alternative is. And the second step, I think, is actually probably, no, the second step isn't too bad. The hardest step, I think, is the fourth step. The second step corresponds to finding the critical value corresponding to the alternative for the given alpha. And what that means is basically determining these Z values that I've been a little bit hand-wavy about. So the critical value is going to be these Z's, the Z alpha over 2 and the Z1 minus alpha over 2 in the case of the two-sided alternative, as well as the Z alpha and Z1 minus alpha in the one-sided alternative. Then after you've determined what your critical value is, and these critical values, for people who are more familiar with this stuff, essentially all you're doing is you're finding the Z statistic corresponding to that alpha value for a normal distribution. So the critical value, let's say alpha were 0.05, this Z of 0.05 is going to be negative 1.65, I think. Yeah, and then, yeah, exactly. So the third step of the critical value method is to determine the rejection rule or the rejection region. And the previous slides I showed with those images are really going to allow you to do that. So for example, if we go back to this one-sided alternative to the one on the left, the rejection region is going to be any X bar value, so any sample averages that we find that are below the Z alphas that we've computed. And yeah, so it's going to be the red areas, the rejection regions. And finally, step 4 is going to be to calculate the test statistic. And this test statistic is based on, for the population mean, it's based on knowledge that we have regarding the distribution of averages. But for now, let's just, yeah, we're just going to use the formula for it because it's a little bit hard to explain where the formula comes from. But yeah, it's based on the central limit theorem. Then finally, once you've gone through all of this, you're going to be able to state the conclusion of your hypothesis test. And since I'm sure this was really unclear, we're going to go through an example, and hopefully that'll make things clear. So the example is going to involve a group of researchers that thought that there was a new diet that might help lower cholesterol levels. So what they did was they knew that the average cholesterol level in the general population was 188 with the standard deviation of 9.8. So that's information that's known. And what this group of researchers did was they took a random sample of 10 people that they knew were on the new diet, and they observed these 10 cholesterol levels. So the goal of this research group was, okay, we hypothesize that the new diet will help lower cholesterol levels, but does it in fact lower cholesterol levels? They needed to collect evidence for this. So in this case, that step 1 of the critical value method was to specify your null and alternative hypotheses. So the null is that the people on the diet are going to be having the same cholesterol level as the general population. So the null value is equal to 188. And in this case, we're actually going to be conducting a one-sided hypothesis test because we're interested on whether or not the new diet helps lower cholesterol levels. So our alternative is going to be, is the new diet cholesterol levels lower than 188? So again, putting this all up, the two hypotheses are going to be the null and null alternative, which we've mentioned. The test statistic, as I mentioned, is based on things that we know about the sample mean. But essentially, all you're going to be doing is plugging in the sample mean for those 10 cholesterol values that they collected on the random sample of people on the new diet. And by just plugging that in, you can get the test statistic because we know the null value and we know what the standard deviation is, and we also know what n is. The critical value in this case, I don't think I mentioned what level I wanted to do it at, but we're going to assume that the significance level is 0.05. So once you've collected your test statistic, which again, we have all of the information for because we know what X bar is, it's just going to be the average of those 10 cholesterol levels that I put up there. Once you know that, you know the null value, which is 188. We know the standard deviation because I gave it in the previous slide. The critical value is going to be negative 1.64, I think, because the significance level is 0.05. The decision rule for this one-sided test is that we're going to reject H naught, we're going to reject the null if our test statistic is less than the critical value, and we're going to fail to reject the null if the test statistic is greater than or equal to the critical value. So I want to just show the slide I showed with the rejection region again. So right now we're trying to conduct a test similar to the one on the left side. And notice again that we have our critical value, which I said was going to be something like negative 1.64. And we're going to be rejecting the null whenever our test statistic, so I was denoting that as Z, is less than Z alpha. So that's our rejection rule. These images are really, really good to understand the directions, but sometimes it can get a little bit hard to remember everything. But yeah, that's why our rejection rule is reject the null whenever the test statistic is less than that Z alpha. So I'm going to go back to that slide. And then again, yeah, we're going to be failing to reject the null whenever the observed test statistic is greater than or equal to that Z alpha. And the reason for these rejection rules is actually pretty intuitive when you think about when you're going to be rejecting the null and when you're going to fail to reject the null. You're going to be rejecting the null when observing this test statistic, which is really just based on the sample mean, is really, really, when the probability of that is really, really small. So if you go back to these images, once you get past this threshold, let's say I observe a value on the very, very left tail of this, the probability of observing that is going to be very, very small given this entire distribution. And that's a situation where we're going to want to reject the null because it just seems so implausible. On the other hand, if I don't know, let's say the test statistic is equal to 0, that's actually pretty likely given this distribution. So that's a situation where I'm not going to want to reject the null. Okay, so this was our decision rule, this is our setup, and now we can actually go through and conduct the hypothesis test for our example. So this kind of helps quantify the entire setup. Basically, we know the mean is 188, the standard deviation is 9.8. Yeah, I think that's all I want to say about this slide. So here we're calculating our test statistic. This is the slide where we're doing that. The test statistic, as I mentioned, all that we're doing is plugging in the values that we already know. So the formula for this Z is going to be equal to X bar, which in this case is 180.8. So when I take the average of those 10 points that I had included in previous slides, we get 180.8. The null value in this case is that 188. And then we're dividing by the square root of the standard deviation, which I told you all was 9.8, divided by n, which is 10 in this case. So we end up getting that our test statistic is equal to negative 2.32 for this example. So again, this is helping visualize this idea. We're getting negative 2.32, which lies all the way down there. So this is us going through all the steps for this hypothesis test. We've actually gone through most of these steps already. We found that the test statistic was negative 2.32. And as I mentioned, our critical value for this significance level is just negative 1.64. Since our rejection rule was that we were going to reject the null hypothesis whenever whenever our test statistic was less than the critical value, the result of this hypothesis test is that we're going to reject the null. And you can see this in step 4, that negative 2.32 is less than negative 1.645. So if we're again imagining that curve shape, the test statistic that we found for our sample is so far to the left that we're finding that the probability of observing that value is pretty low, and that's enough evidence to reject the null. So the conclusion of this hypothesis test is that it seems like there is enough evidence based on our sample to conclude that the new diet significantly lowers cholesterol levels. So one thing to notice is that, as I mentioned, we had set alpha to be equal to 0.05, and that has impacts on those Z values, so the critical values. I said that when alpha was 0.05, the critical value, so that Z alpha, was equal to negative 1.6465, negative 1.645. So one thing that's interesting to notice is what happens as we change alpha. And remember again that those alpha levels were the probability of a type 1 error. So if I, as a researcher, say, I want to make sure that I'm not making type 1 errors, so I start to set alpha to even lower levels, what happens to the results of our hypothesis test? As you notice, as you set alpha to lower and lower values, what ends up happening is that your critical value becomes smaller and smaller. So it starts shifting more and more to the left of your curve. And so even though at alpha 0.05 and at alpha 0.02, you reject the null hypothesis because your rejection rule tells you that you should be doing this, when alpha reaches the level of 0.01 or 0.005, you fail to reject the null hypothesis. So when you're constraining the probability of a type 1 error to be so small, what ends up happening is that your hypothesis test is showing you that you no longer have enough evidence to state definitively that, yes, we are going to reject the null hypothesis. We end up needing to just fail to reject the null hypothesis. And so as a researcher at this point, let's say for some reason you are still in the data collection part, you might be interested in being like, okay, but it's very important to me that my alpha levels are set at 0.01. What can I do if I'm always failing to reject the null? This is an indication that I don't have enough evidence. What can I do to get more evidence? Well, one, we're going to talk a little bit about this, but one suggestion is just maybe to increase your sample size, perhaps think a little bit more about your type 2 errors and what you can do about those. So as I've been mentioning, the significance levels are very important, and you've probably come across these without even maybe knowing that they're called significance levels. Significance levels are denoted as alpha, and it's the probability of a type 1 error. And another error that we care about, though, is also the type 2 errors, because based on that original table that I showed, a type 2 error is showing that you're making a mistake. So the mistake that's being made with the type 2 error is that you're failing to reject the null, even though the alternative is true here. And here you'll notice that instead of using HA, I'm using H1. The reason why type 2 error probabilities are also somewhat of a concern for individuals conducting hypotheses tests is because they're very closely related to power. So power, if we let type 2 errors be beta, power is just going to be 1 minus beta. And the power of a hypothesis test is going to be the probability of rejecting the null, given that you know that the alternative is true. So essentially, this comes down to the probability of detecting some sort of, let's say, association, if that's what you're testing for, or detecting some sort of difference, given that there is, in fact, a difference. So as a researcher, you definitely want a study that has high power. And having high power, since it relates so closely to type 2 errors, means having low type 2 error probabilities. So that's where you can kind of see this trade-off coming into play. As a researcher, you're going to want low alpha values and low beta values, because low beta values mean high power. But yeah, you can't get everything, unfortunately. So a lot of the time when you're setting alpha, I mentioned that it's set at 0.05. And so an interpretation of this is that this is setting the maximum chance of incorrectly rejecting the null when it is in fact true at 5%. So that's just an interpretation of that alpha value. Power, on the other hand, as I mentioned, is the probability of correctly rejecting the null when the alternative hypothesis is in fact true. So if you're setting beta, let's say, to 10%, that means that your power is 90%. And what having a power 90% or a beta of 10% is equal to is that you're saying that you're willing to accept a 10% chance of missing an association of some effect size when it in fact does exist. So again, this beta is the probability of missing the association when it in fact exists, or failing to reject the null when the alternative exists, when the alternative is true. So a very good question, I think, is, okay, we know about these alpha and betas, like what should we set them equal to? And again, this is going to depend on the application. There's a lot of tables showing different combinations of alpha and beta and the different sample sizes that you need for testing all these things, because they do depend on the sample sizes, as I'll talk about. Usually for most experiments, alpha ranges anywhere between 0.01 and 0.1, and then beta ranges between 0.05 and 0.2. And beta ranging between these two values means that researchers generally want their power to be somewhere between 80% and 95%. And as I mentioned, there's going to be settings where it's important to minimize type 1 errors and settings where it's important to minimize type 2 errors. So this is very, very closely linked to like the sensitivity and a specificity of a test. Sometimes when you're getting some sort of test done, you're gonna wanna make sure that you minimize those false positives. And in other situations, you might be more concerned about false negatives. It's the same sort of idea. So as I mentioned, there's a lot of things that can impact your type 1 and type 2 error probabilities. Of course, alpha and beta, as I mentioned, tend to be inversely related, but there's things that you can do to minimize one of them by holding the other one constant, for example. So if we consider this test here, I know that it's a little bit confusing to see the two diagrams, but let's just focus on the size of those alphas and betas down there. And we're basically going to be exploring our options in order to minimize one or the other, the alpha or the beta. Because yeah, there's a trade-off between the two of them. So a lot of the times what's done in many, many studies is that they fix the alpha value at some level, as I mentioned. So usually it's fixed, the two values I've heard about the most are like 0.05 and 0.01. So usually you fix alpha first, and then you go and try to do different things to change your beta, so to minimize your beta. And we're gonna be exploring what all of those different things are. So one thing that you can do to decrease your beta for a given alpha value is to modify the effect size. So let's say that I want to determine whether two things are different from each other, and I'm trying to determine, I don't know, if there's like a 1 unit change between them versus a 50 unit change between them. Detecting whether or not there's a 50 unit change between them is going to be easier than detecting whether there's a 1 unit change between them or difference between them. And so one way of decreasing this beta or type 2 error probability is by increasing the effect size. So you're going to be getting a higher power the higher your effect size is, because it's just easier to detect whether something that's 50 units greater, let's say, versus something that's 0.01 units greater. And this idea comes down to shifting, if the effect size is the middle of this first curve of the H naught curve, so it's 0, and originally it was at approximately 3, so the effect size would have been 3. If you switch the effect size to instead be 4, then you end up finding that your type 1 error probability is still alpha, but now your type 2 error probability is going to be smaller. Something else that can affect your statistical power. Yes, over.
But my effect size in this case is something I measure, right? You said like you want to measure the distance or.
Yeah, but you're the one.
So this is something I measure. I do not
Exactly.
value more to the right or to the left.
No, but you're the one though that's going to be determining how big of an effect you want to capture. Like you're the one specifying the hypothesis. So you're the one that can determine whether you're interested in capturing a very, very small difference between things, or if you're interested in knowing just how big they are. So for example, it's going to be easier to capture, let's say that the hypertensive smokers, and going back to that example, have an average cholesterol level of like, I don't know, 190. It's going to be easier to capture that than to capture the situation where the difference is, I don't know, 200. It's where the average level is 210.5, because that's much closer to that 211.
Yes, but as I said, this is something you measure. You measure the levels of patient. You cannot then later say, like.
Oh, I see what you're saying. Okay, no, I get your question now. That's a great question. So I think that when you set up your question in such a way where you kind of know, let's say that hypertensive patients, let's say that their cholesterol levels are very, very close to that 211, and yeah, you're not going to be able to increase that effect size. You're not going to be able to play around with that. So in that case, you're going to want to increase power in other ways. You might want to change your sample size. You might want to change your alpha value. You might want to measure the standard deviation differently, and so forth. That's a good question. Yeah. So yeah, in a situation like that, you might actually want to make sure that you have a greater sample size, because what the sample size ends up doing is that if you increase the sample size, the distributions that you're looking at actually become narrower. So in these illustrations, what ends up happening is that they become kind of skinnier. And so at a given alpha value, so let's say that the red section is equal to 0.05, if you increase the sample size, then the values become more concentrated, and this is going to lead to reductions in the beta value or increases in power. So as I mentioned, what most researchers do is they set an alpha value and then try to go back and do things to impact their power. Sometimes it's going to be easy to do some of these things, and in other settings, it's not going to be easy. Power is going to depend on the significance level. As I've mentioned several times, there is a trade-off between the two of these because they represent the probability of type 1 and type 2 errors in the case of alpha and beta. And so alpha and power are also going to be related to one another. If you increase your type 1 error probability, then that means your type 2 error probability is going to decrease, and so power will increase as well. With effect sizes, again, if you can formulate your question in such a way where the effect size that you're trying to capture is rather large, then that's going to help increase your power as well. If for some reason the spread so the standard deviation of your population decreases, then that's going to help increase the power as well. And then what most people do is, I think most of these are centered around sample sizes. If you increase your N, or your sample size, that's going to lead to increases in the power as well. So that leads us to the final slides for this unit. I didn't include too much on sample size calculations because there are a lot of different formulas, and I think that this is a topic that is really going to depend on whatever research you're conducting. I just hope that by the end of this, what we kind of get out of the sample size calculations is that they're going to depend on a lot of things. They're going to depend on the alpha values we were talking about. They're going to depend on the beta values we're going to talk about. But yes, the formulas that I'm including here are somewhat elementary, and yeah, they don't help capture situations that are really, really important. I know that some of my friends in biostatistics, like their entire dissertations are on these sample size calculations, because once you get into specific types of study design, your sample size calculations not only do they become really important, but they also become really, really complicated. So yeah, I didn't want to go into too much detail on this, but relating sample size calculations to hypothesis testing, if you have a one-sided test, you're going to use a slightly different formula than if you have a two-sided test. Basically, your formula for a sample size calculation is going to depend on the variance of your original population. So this is something that is usually assumed to be known. And then it's also going to depend on the critical value that's determined by that alpha. So what I've been calling that Z 0.05, for example, if alpha is 0.05. So, and it's also going to depend on that critical value evaluated at your beta or type 2 error probability, so that Z beta. And then the denominator of the sample size calculation is going to depend on the effect size. So in this case here, we see that the one-sided test sample size calculation varies from the two-sided test sample size calculation just by that Z alpha. So for a two-sided test, you need to plug in Z of alpha over 2 instead of Z alpha. And what conclusion this leads us to is that for a two-sided test, you're always going to need more people than for a one-sided test, because Z of alpha over 2 actually has a higher magnitude than Z of alpha. Oh, yeah. 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 Yeah, you're gonna have to change these calculations slightly if you don't have that information. It's a great question. And yeah, that's why, yeah, these calculations, a lot of the times it's hard to estimate a lot of these things. Like as you were saying, it's hard to estimate, for example, the effect sizes. Sometimes you don't know. So I've also seen sample size calculations that aren't written in this way. They're written with respect to other things we care about. I decided to include these because I think they relate pretty well to what we were talking about with hypothesis testing. But yeah, for example, a sample size calculation for a proportion is going to be different than this, and they can be formalized differently as well. Yeah. So just to go through a couple of examples. Our first example is that we're testing for weight loss, and we're going to be conducting a one-sided test. The significance level that we want is 0.005, and we're trying to determine how large of a sample we should be able to collect to detect some sort of 5-kilogram decrease in weight with probability 90%. So in this case, we are actually able to specify the effect size because, as it's been mentioned in the question, we want to be able to detect whether or not there's been a 5-kilogram decrease in weight. So if we outline all of the ingredients to this example, in this case, the desired power is going to be 1 minus beta. So it's going to be equal to 0.9 because we said that we want to be able to detect this with probability 90%. So we want to make sure that we're detecting an association when it in fact exists with 90% of the time. The effect size that we want to detect is going to be equal to 5 because we want to detect a 5-kilogram decrease. The significance level here is going to be 0.05. And as you were just mentioning, sometimes you don't know the standard deviation, but if other studies have shown that it's a specific value, you can use that. I've definitely seen formulas that help account for that uncertainty. But let's just say here that what we think the standard deviation is 10. So the question we have is, okay, we want to have this experiment. How many people should we recruit for the experiment, taking into account that it's a one-sided test? So what we would do is we plug in all of the values that we have into this equation. So as I mentioned again, the effect size we want to capture is 5, so that's going to be our denominator. And then our numerator is going to be the product of the standard deviation, which was 10 squared, times the the squared value of the critical value evaluated at our type 1, or at our significance level, which is 0.05, plus the critical value evaluated at the beta level, which in this case is going to be 0.1 because we wanted a power of 0.9. And yeah, these critical values, I know I've been really hand wavy about it, but you can just find them by using like a Z distribution, Z table, which has all the critical values for given values of alpha and beta. So when you plug all these things in, you end up finding that you need a sample size of at least 34.3 people in order to be able to detect these things. So when you're conducting your experiment, you'd want to make sure that you have at least 35 people. One thing to note about these things, and again, I've also seen sample size calculations that try to account for this, is that you need 35 people on which to conduct the analyses on. So if you were a researcher and you were interested in all these things, you wouldn't want to go and simply recruit 35 people because you might lose a lot of people to follow up, you might have compliance issues, and so forth. So in calculating sample size, you also need to add up some sort of buffer for that, or try to modify the sample size based, let's say, on your retention rates or on the proportion that you believe are going to be available at the end of the study. So even though sample size calculations are very, very useful and very powerful, it really takes a lot to make sure that they're capturing what we want them to capture. I included another example that I can go through pretty quickly in the interest of time, but the idea here is that we want to test whether the null value is equal to 12 or whether it's greater than 12. So in this situation, the power that we want is 0.80, and for some reason, in this example, we've just set the effect size to 2. The significance level is again 0.05, and we know the variance. So very, very similar to what we did in the previous slide. We're just going to use our formula for a one-sided test. The only thing that's changing here relative to the previous example, of course, aside from the effect size and the variances, are the power. In the previous example, I had put a power of 0.9. In this one, the power is 0.8. So that means that our beta is going to be slightly higher. It's going to be 0.2. So that Z value is going to be different than the previous one. So in the previous one, we had a different value here. But anyways, you end up finding upon doing all these sample size calculations that N needs to be greater than 56. And the reason why I included this example was because I really like the plot that's on the right side. What it's graphing is that on the x-axis, it's graphing the power against the sample size. And so we had set power in this example, I think, to be 80%. If we were to set it, yeah, 80%. If we were to set, and that leads us to a sample size of approximately 56. If we were to set it to be, let's say, 0.7, we'd find that we need a smaller sample size. So smaller power, smaller sample size. If we want greater power, we're going to need more and more people. So I think this plot is just showing you the relationship between the two of them. And I could have also placed other curves to help show the relationship between other variables. But I liked that this one shows that it's not exactly a linear relationship between the two either. There's points towards the end, especially if you want to get from a power of 0.9 to a power of 0.95, you're going to have to really recruit a lot of people in order to accomplish that. So these are just the summarized versions of our sample size calculations without using all the math notation, but it represents the same formulas as we looked at before. And as I mentioned, there's a lot of different formulas out there, and formulas that are probably more suited to account for specific needs and specific research questions. But yeah, one thing I did want to really iterate was that even though these sample size calculations are nice because they're giving us a specific value we can focus on, it is necessary to account for other factors like dropout or low response rates. And I wanted to finish up with this post because when I was learning hypothesis testing in one of the classes here, the professor ended with this, and I thought it was kind of funny because she had just spent like an hour talking about hypothesis testing. But this person is basically saying that they hate hypothesis tests, and I think this argument as to why we shouldn't be using hypothesis tests is actually very similar to the argument against p-values. But I think the takeaway theme that I like from it is that they're basically advocating for the use of confidence intervals because they're telling us that hypothesis tests in a way, even though they are useful, sometimes they're just telling us whether we fail to reject the null or whether we're rejecting the null. Sometimes using confidence intervals can actually be very, very powerful because they can give us ideas about the magnitude, and they also allow us to test other things as well. So even though I don't mean to be like, oh, everything we talked about is irrelevant, I do think it's important to keep in mind that there's other ideas that are very relevant and can help us accomplish our needs as a researcher. Thank you so much. We still have a couple more of these series left. On Thursday, we're going to be talking about cohort studies and case control studies. And then Tuesday, June something, we're going to be talking about proportions and means. I think it's Tuesday, June 4th, actually.
It is.
Thank you.
Anybody have any questions in-house or online?
Not really a question, maybe just to reiterate that, like, it's still working in my brain, so if something is wrong, it's wrong. But basically, when I haven't set up an experiment and I've collected several data points from patients, for example, and I have different observations, like different measurements, like maybe blood pepper, or let's go with the genetic assay that might be easier. Like I have different measurements of gene expression levels of different genes, and usually what people are doing is like looking for the p-values for the type 1 error. But and then they simply classify by this is significant, this is not significant. The not significant one, I could go over these and could check for the power if they fail because of missing power or because really they fail to reject the null, right? Because you said like, because for gene expression levels, for example, I might have like, if I have two different groups of patients, I have one patient group has very high levels of gene expression, the other very low. This would contribute to a very low, to very high power because the difference of trying to capture is very high. In other ones, in other genes, that might be very similar, but so decreasing my power. So there could be still a difference, but I do not capture it because my sample size is so small and the difference between the gene expression levels is also so small that the power is so small. So they're not really non-significant, they're simply, they might fail because of the, not enough power in the analysis.
Yeah,
you might want to look at these again with a higher sample size to make a real conclusion about these genes, right?
Yeah, so I think there's actually a lot of different things in what you said. So yeah, it's very possible that some that were found to not, like where the p-values were, where you didn't reject the null, it's very possible that that was a result of low sample sizes. A lot of the times too, when you're running these hypotheses tests, in some like gene data, and I really don't know the data very well or what you guys are running, but one thing that a lot of people don't do is when you're testing multiple hypotheses at the same time, it is necessary to account for that, so to kind of correct for that. And there's different corrections that are used. One of them is called Swan-Ferroni correction, and things like that might be of use. So when you're, sometimes when you're testing things like, if you're testing just one hypothesis about one population parameter, this isn't a concern, but when you're testing lots of parameters at the same time and you're making lots and lots of hypotheses, it is necessary to make corrections for those.
Okay, so this would capture the type 2 error,
So-
or this kind of type 2 error I was explaining, this multiple testing correction. Like
Well, no, that's what I wanted to ask you more about, because I had missed a little bit of the because I was trying to catch as much as I could. So basically, you have two different groups, and you're trying to find.
Yeah, for example, I have two different groups, and there might be differences in gene expression for different genes, right? So I have let's say I capture like gene counts, how many counts or how many genes are expressed in this group versus another.
Okay.
And for some of these genes, the difference might be very obvious and very strong. For some of them, it might be not as strong.
Yeah.
The sample size is not enough to give you enough
Exactly.
power for that particular gene. So
yeah,
I kind of have
exactly.
an experiment in an experiment.
Exactly. No, it's very true that when the sample size is very low, you're gonna need very, very big differences in order to detect those things. It's not going to be as easy as before. That's definitely
the
true.
example with the hypertension might be, or none of this might be, if you have like these two averages, but then you have like male and female, and your average is of course not capturing this. But then if you would split it into female and male, you might end up to have a different power because the distance between your measurements might be different, right? That's
well, and something else to keep in mind is that I know in a lot of my team research teams or whatever, we have kind of shied away from using those p-values. Like a lot of people on the team don't like to use them because sometimes when the sample sizes are so big, like pretty much anything's going to be statistically significant. And so they prefer to use things like standardized differences, where you're taking like the average of one group minus the average of the other group, and then like a pooled standard error measurement. They prefer to do that because they feel like that better captures these differences between two groups. So yeah, I mean, I think those are all important considerations to keep in mind when you're running these things. And yeah, I think a lot of people aren't actually thinking about them when they're doing it. Yes. No, yeah, they're actually both analogous because you can show that, yeah, a 95% confidence interval is really capturing the same thing as the critical value method, because the test statistic that you're using to test these values is also kind of embedded in these confidence intervals. I've always preferred confidence intervals. I don't know why. Honestly, yeah, and I understand if some of this was pretty hand wavy because those like rejection regions and like the critical value method usually takes like 1 or 2 classes to teach and to really properly teach people how to go through it. And I mean, yeah, constructing confidence intervals isn't an easy task either, but I just think when you're first learning about hypothesis testing, it's really intuitive to just ask yourself, okay, does it fall in this region or does it not? But yeah, they are including the same question. They are including the same information. So the result of the confidence interval method is always going to give you the same as the critical value method. Yes, they're mathematically the same.
Yeah. I have a question from somebody on Zoom. They say, I understand we use a method like the student t-test when we don't know the mean and an STD of the overall population, like when we have 2 groups, for example, an experimental group having a diet and a control group with traditional diet. In this case, what's the key difference between the t-test and an ANOVA?
Okay, I didn't catch the whole question, but yeah, when you don't know the standard deviation, that's going to impact the statistic that you end up using. So I know I was a little bit hand wavy about this, but in your confidence intervals, so in the confidence interval example that we looked at, the t, I was using the t statistic because we didn't know the sample, the standard deviation. We were using the standard error. So in that case, you need to use the t statistic. If you know the standard deviation, you can actually just use the corresponding value from a normal distribution. what's a lot of the times people don't even distinguish between those two things, even though they should. Because when you have a large enough sample size, the t-distribution converges to the regular values that are used. So they end up being the same thing when you have enough people. But I think there's images showing that when the sample size is small, there are actually some differences between the two. Thank you.